Hello, everyone. My name is Xiaowei Zhang from the University of Hong Kong. In this video, I will give a tutorial on surrogate-based simulation optimization. This is joint work with Jeff Hong from Fudan University. Simulation optimization concerns a class of optimization problems whose objective functions and/or constraints do not possess an analytical form and can only be evaluated based on noisy simulation samples. Specifically, in this tutorial, we consider the following maximization problem, where the objective function f of x is expressed as an expectation. So here, the capital F of x is a real-valued random variable that represents the stochastic response of the simulation model of interest. Although the distribution of the capital F of x is unknown to us, we assume that the samples can be generated by running simulation experiments. In practice, simulation models are usually computationally expensive to run, and therefore the number of evaluations that we are allowed to perform is rather limited, subject to our computational or simulation budget. Hence, in this area, we are interested in designing sampling algorithms in order to allocate the simulation budget in such a way so that after exhausting the budget, we are able to find a good solution to this optimization problem. Because simulation optimization is has such a vast literature, I would like to refer to the following paper by Michael Fu and Shane Henderson, published in the Winter Simulation Conference of 2017, which gives an excellent account of the long and rich history of simulation optimization. Depending on the nature of the feasible set, the simulation optimization problems actually defines a different treatment and principle for designing algorithms. In particular, if the feasible set is a set of relatively small number of feasible solutions with no inherent ordering defined, then the problem is known as the ranking and selection problem. For example, the feasible set may represent feasible system configurations with regard to how many and what redundant components to use to design a reliable system. Another common setting is that the feasible set is integer ordered, which basically means the feasible set is a subset of d-dimensional integers. In this setting, the feasible set usually has a very large or even infinite number of elements. And the simulation optimization problem that we saw on the last slide is called discrete optimization via simulation. However, in this tutorial, we will focus on the setting where the decision variable is continuous. Our concentration on continuous decision variables does not limit the scope of this tutorial. That's because in general, algorithms designed for the continuous setting can often be applied to discrete optimization via simulation problems. Of course, although the theoretical analysis may need to be adjusted. A variety of strategies have been proposed to solve continuous simulation optimization problems, including sample average approximation, stochastic approximation, and random search. However, in this tutorial, we are going to focus on surrogate-based methods. This is yet another class of strategies for simulation optimization problems. Despite their long history, the surrogate-based methods have gained an increasing interest in recent years. The popularity of the surrogates, the use of surrogates in simulation optimization may be attributed to, first, the flexibility to capture complex surface shapes, and second, the capability to predict surface values in regions where no simulation samples are observed. This latter reason is of particular importance in light of the fact that computational budget is generally regarded as a scarce resource relative to the cost of simulation experiments. Finally, we would like to make a note that there have been several earlier tutorials on surrogate-based methods in simulation optimization. So for example, Russell Button and his co-author did one in 2006. This current tutorial, we aim to bring the readers or the audience like you up to date on the fast developments in this area. Here is the outline of this tutorial. We first are going to introduce several typical surrogates that are widely used in practice, and then we're going to present simulation optimization algorithms that use surrogates as either local approximations or as global optimizations. And they naturally lead to algorithms that are locally convergent or globally convergent. After that, we're going to discuss recent advances in handling computational issues that arise when using surrogates for large datasets. And finally, we're going to conclude this tutorial with remarks on the current research challenges and the potential opportunities. So what are surrogates? A surrogate is also known as a meta model. It is an approximation to the response surface, that is the simulation input-output relationship. The main purpose of using a surrogate is to mitigate the computational burden of running expensive simulation experiments. So in a sense, any supervised learning model in principle may be used as a surrogate. However, there are indeed several considerations that we need to keep in mind when choosing a surrogate to cope with the computational budget constraints. First, the surrogate should possess a simple structure, and it should not require big data for the fitting purpose. And that's because simulation samples are generally considered as expensive to acquire. And second, the surrogate should be computationally easy to fit because it often needs to be updated in a sequential fashion as more simulation samples become available. And third, it should give rise to a predictor in closed form so that the predictions can be computed efficiently, theoretical analysis can be facilitated, and the surrogate can be optimized easily. These three risks, there are three classes surrogates that satisfy the criteria that we have just discussed, and we are going to introduce them in this tutorial. And these are low-order polynomials, linear basis function models, and Gaussian processes. First, polynomials. Because the number of terms in representing a polynomial in multiple dimensions expose, polynomials with orders higher than 2 are rarely used in practice. So by low order polynomial, we mean either the first order, which means linear functions, or the second order polynomials, which are quadratic functions. So low order polynomials are suitable for situations where we are interested in a localized region of the feasible set. So here is a general expression of a second order polynomial. This surrogate may be appropriate if we expect the response surface F has substantial curvature in the region of interest. Otherwise, a first order polynomial, that is linear functions, may be a better choice. In this surrogate. To use this surrogate, we need to estimate the parameters betas using the simulation data. And these parameters can be estimated with ordinary least squares. But I will hold the expression of the OLS solution till the next slide, where a more general setting is discussed. The second surrogate that I would like to discuss is the so-called linear basis function models. If low-order polynomials do not provide a good fit, a natural generalization is to consider this class of linear basis function models. They express f as a linear combination of basis functions. There are a great variety of basis functions, such as truncated power basis or radial basis functions. Similar to low-order polynomials, the vector of parameters, beta, can also be estimated via OLS, which means we are going to use the value of beta to minimize the sum of squared errors. And the solution to this OLS minimization problem can be solved explicitly and expressed using linear algebra. So given the parameter estimate beta hat, the prediction of this linear basis function model is simply computed by plugging in the estimate into the model. And this is yet another linear algebra expression of the prediction from this surrogate. The third surrogate, which is also the most popular one in practice in recent years, is Gaussian process. Gaussian process is also known as a Gaussian random field. It has remarkable success in numerous research areas, such as geostatistics, design and analysis of computer experiments, stochastic simulation, and machine learning. Gaussian processes can be considered as a generalization of multivariate normal random variables. Whereas the linear basis function models represent a frequentist viewpoint, Gaussian processes are indeed Bayesian models. So a Gaussian process is fully characterized by its mean function and covariance function, which is also called kernel. To use a Gaussian process as a surrogate, we start by imposing a Gaussian process prior on the unknown function f. Some people may prefer to state the assumption in a different way, namely the f is a sample path or realization of the Gaussian process. Both actually mean the same thing, which is for any finite set of design points, x1 through xn, the vector of function values f of x1 through f of xn has a multivariate normal distribution with a mean vector mu and covariance matrix k, which are given as follows. In this figure, it shows several realizations or sample paths of a Gaussian process. And the true function, which is unknown to us a priori, is just one of them. The mean function. From a modeling point of view, the mean function is used to encode one's prior knowledge about the overall shape of the response surface. It is usually chosen in one of the following three ways. First, we can set the mean function to be simply a constant. Here, the constant represents the overall surface mean. This is possibly the most common treatment in practice. One may even set the c equals 0 if no or little prior knowledge is available to us. The second choice of the mean function is to set it to be a linear combination of a given set of basis functions. And third choice is to set the mean function mu of x to be a function derived from a simplified model of the same stochastic system that the regional simulation model aimed to describe. So for example, if the regional simulation model is a complex Q model, the mu of x may be derived in closed form based on a highly stylized Q model. So we will revisit this point later in the tutorial. Covariance functions or kernels. So here I would like to introduce two popular classes of kernels. One is the Gaussian kernel, which shares the same form as the probability density function of a Gaussian random variable. A second class is the Matin class. It is Matin kernels. Its general expression is fairly involved. It involves mathematical special functions such as the gamma function, and this is the so-called modified Bessel function of the second kind. So despite of this sort of a complicated general expression, in practice, people usually set the parameter nu to be half integers, that is 1/2, 3/2, or 5/2, and so forth, because by doing so, the expression can be reduced to a much simpler form. But due to the limit of the space, I'm not going to review them in this tutorial, but they can be found easily either online or in our article. Okay. Among the parameters that defining the Matin kernel, the parameter nu is the most important one. It is called the smoothness parameter because it determines the order of differentiability of the sum of paths of the Gaussian process associated with this kernel. So here in these three figures, I plot the sum of paths that are generated from Gaussian process associated with the Matin kernel having the smooth parameter set to be 1/2, 3/2, and 5/2. Apparently, as we increase the value of this parameter nu, the sum of paths becomes smoother and smoother. After we specify the mean function and the covariance function of the kernel, then we can use the Gaussian process to help us to do the prediction. And that's this technique is often referred to as Gaussian process regression. So in particular, if we impose a Gaussian process prior on the unknown function f, and if we assume the simulation noise is an independent Gaussian random variable with a known variance, then it can be shown easily that the posterior distribution of the f is also a Gaussian process. So in this figure, you are looking at the sum of paths that are generated from the posterior Gaussian process. So obviously, one notable feature of this figure compared to the previous one is that the variance of this posterior Gaussian process is much smaller, and that's because we have made several observations of the function value. So one very nice property of Gaussian process regression is that the posterior mean function and the posterior covariance function of this posterior GP process, Gaussian process, is available in closed form, and in particular, we can use the posterior mean function for the purpose of prediction, and it is given again with its fairly simple linear algebra. So here, I just want to point out that this matrix K is a covariance matrix induced by the kernel K, evaluated at this n design points, and this matrix sigma is a diagonal matrix, and the diagonal elements of this sigma matrix represent the variance of the noise at various design points. So we will come back to this matrix later in this tutorial when we discuss how to handle the computational issues associated with large datasets. So far, we have treated the simulation model as a black box that performs nothing but transforming inputs to outputs. By doing so, we have implicitly assumed that the only data available to us when constructing a surrogate are simulation outputs. Nevertheless, there possibly exists auxiliary information in practice that we can leverage without much extra computational overheads to enhance the prediction capability of the surrogate. And in the following, I will present two general approaches. The first one is to enhance surrogates with a stylized model. Simulation models by design are used to describe in detail the interactions between different components that constitute a complex stochastic system. However, the main features of the same system may well be captured by a stylized model that use analytical expressions for the performance measure of interest. Considering the following example taken from one of our previous papers, joint papers, in this example, the patient, this paper considers a complicated queue network model in hospital, where the patient flow through various medical units are modeled as a queue network. The finite capacity of one medical unit to accommodate the patients often leads to blocking behavior, which meaning that it will block patients from entering, making them stay in the upstream medical units, even if the service has already been accomplished, already been completed there, and possibly creating further blocking. A stylized model, however crude it may appear, is to decompose the network into isolated independent units by discarding the interactions and model each unit as a multi-server queue. By doing so, the performance measures such as the average length of stay can be derived in closed form for this highly stylized model. So stylized models are often used to gain managerial insights into the inner workings of the stochastic system of interest, but they can be easily incorporated to construct a surrogate for the simulation model. So let's the psi represent the analytical expression derived from a stylized model. Then we can simply add this function psi to the set of generic basis functions, and then use use all of them either directly in the linear basis function model or use them to construct the mean function of a Gaussian process. The key idea here is that one may use a crude model to capture the overall trend of the response surface. Conceivably, the residue after detrending will have fewer variations, and therefore it will be easier to fit by a surrogate. So in this figure, you are looking at a very simple demonstration of the increase or enhancement in the prediction capability by incorporating a very simple stylized model into a Gaussian process regression. The second approach to enhancing surrogates is to take advantage of gradient observations if they are available. Given simulation outputs for an input value x, an estimate of the gradient of the response surface with respect to x can often be obtained with a negligible additional computational overhead. This kind of direct gradient estimation, which is in contrast to finite difference approximations, requires no additional simulation, and it can be achieved by infinitesimal perturbation analysis or the likelihood ratio method. Suppose although the technical details of this approach are somewhat involved, the idea is simple. So given a surrogate for the response surface f, this surrogate actually induces another surrogate for the gradient surface. Okay, so effectively what we have is a joint model for both the response surface and the gradient surface. So if we are able to observe not only the simulation outputs, which are the observations of the response surface, but also the observations of gradients, then we can jointly estimate the parameters using these two surrogates and those two sets of observations. And by doing so, it can greatly enhance the prediction capability of the surrogate. So this direction has been explored. There have been several studies along this direction, discussing this idea by using different surrogates such as linear models, linear basis function models, or Gaussian processes. So now, having covered the typical surrogates that are used in practice, especially the Gaussian process, now we move to the second part of this tutorial. Based on the convergence guarantees, simulation optimization algorithms may be classified into the following two categories: locally convergent algorithms and globally convergent algorithms. So by global, we mean that the algorithm converges to a global optimal solution, whereas local means the convergence occurs only to a local optimal solution or a stationary point. While global convergence seems more suitable, more desirable, but it requires exploring the entire feasible region in the limit. In many practical situations, however, the simulation budget is limited and only allows us to explore maybe only a small proportion of the feasible region. So in this kind of situations, local convergence, which requires only local information, may become more meaningful, have some advantages. So we are going to, there are many locally convergent algorithms that have been developed over the years. So in the following, I'm going to just cover two basic ones. The first one is called response surface methodology, RSM. RSM has a long history. So it was originally developed in it was originally developed by Box and Wilson to optimize the operating conditions in a chemical process. So it typically consists of two stages. In the first stage, it runs a number of experiments in a local region of the current solution, and then fits a first-order polynomial surrogate. Given this first-order polynomial, we can effectively find a direction of ascent direction, and along this direction, we may be able to find a better solution. Okay. So we are going to repeat this process several times until the first-order polynomial is no longer adequate for the response surface. Up to that moment, this RSM method will move on to the second stage, in which we are going to fit a second-order polynomial. And then after that, we're simply going to maximize this second-order polynomial over this relatively small region of interest. Despite the popularity of RSM, it is rather heuristic in nature. So for example, the procedure involves a lot of human judgment. So first, in each iteration of the RSM, a surrogate needs to be optimized in a local region, but the local regions are determined mainly by experimenters based on their experiments, based on their experiments. Also, the transition, so transitions between the first and second order models typically also depend on human experiments, human experiments. And it is not clear whether a second order model may transit back to a first order model if it is found inadequate. Also, because RSM is typically used for very expensive simulation or real experiments, large sample properties such as convergence are not clear. Therefore, in 2013, Chan, Hong, and Wan proposed to incorporate the trust region method from the nonlinear opposition literature to address the heuristic nature of RSM. And the method or algorithm that they proposed is called the strong algorithm. So the strong algorithm works as follows. In iteration k, let's use the xk denote the current solution, and delta k denote the size of the so-called trust region, which is actually a d-dimensional ball centered at xk. And this is the radius of that ball. In each iteration of the strong algorithm, it does four steps. In the first step, we fit a local surrogate, let's see R of k, around sk. So because this is simply a local surrogate, so it's either a first order polynomial or a second order polynomial. Depends on the size of the trust region. If the trust region is large enough, determined by a prescribed threshold delta tilde, then we're going to use a first order polynomial. Otherwise, we use second order. After fitting this surrogate, we're simply going to maximize this surrogate over the trust region. So here, this B of xk and delta k is the trust region. It is, as I mentioned earlier, it is a d-dimensional ball centered at xk with a radius delta k. So this maximization can be done easily because, after all, the objective function here is either a linear function or a quadratic function. So in the third step, we are going to run the simulation models a number of times at sk star, and then use the sample average to estimate the function value at that place. And finally, we'll conduct two statistical tests to help us to update the value of sk and delta k. So roughly speaking, one test will test whether this candidate x star is significantly better on xk or not, whereas the other test will test whether the surrogate works well or not. So here are the details of these two tests. If the candidate is not significantly better than sk, then we're not going to update the solution. We're going to simply set sk plus y equals sk, and we're going to shrink the trust region by decreasing the radius. Otherwise, if this candidate is indeed significantly better, then we're going to go to the second test. In this test, we compute the ratio between the observed improvements and the predicted improvements. So if this ratio is large, which means the surrogate works well, then we're going to update the current solution sk plus 1 to the candidate and increase the radius. If this ratio is small, which means the surrogate works poorly, then we're not going to update the solution. And at the same time, we are also going to decrease the trust region. And if the ratio is somewhere in between, then that means surrogate works somewhat well, but not too well. Then what we're going to do is we're going to update the solution, but we're going to keep the trust region for the same. So now let's make a simple comparison between the strong algorithm and the RSM that we mentioned earlier to highlight the rigorous nature of the strong algorithm. So first of all, let's notice that the strong algorithm uses the trust region as a local region, and its size, delta K, is updated adaptively based on statistical tests. Okay. Further, the transitions between the first order and the second order surrogates are based on the size of the trust region. If it is larger than threshold, then we use the first order, otherwise with the second. This transition rule allows the algorithm to transition between the two surrogates in both directions. Therefore, the strong algorithm removes the human involvement, making the algorithm much more rigorous. And furthermore, it can be proved that under certain technical conditions, the strong algorithm converges to a different point in the limit. So now let's move on to the third part of the talk. The third part of this tutorial, the globally convergent simulation optimization algorithms. So there are mainly two strategies for using global surrogates, such as linear basis function models and Gaussian processes, to solve a continuous simulation optimization problem, and that will lead to globally convergent algorithms. And these two strategies differ with each other depending on whether the design points x1 through xm are chosen in a static fashion or in a sequential fashion. By static, we mean that the design points are all selected before any simulation, once for all. With no observations of the response surface being available, a primary design principle of choosing these design points is to cover the design space or feasible set as much as possible so that most part of the response surface can be recovered after the observations are made. Typical experimental designs include lattice designs and space fitting designs, and I would like to refer to this classic textbook on experimental design for details. Given an experimental design, we will run simulations at each design point, possibly multiple times, and then use the estimate to fit a global surrogate, such as a Gaussian process, and then optimize the predicted surface, f hat, which is a deterministic function. And at that point, we can use any numerical optimization algorithm to do so. Recent advances in simulation optimization with surrogates as global approximation are dominated by sequential experimental design, meaning that the design points are determined one at a time after each new observation of the response surface is made. Each new design point is selected based on, first, the updated surrogate that reflects the previous observations, and second, certain criteria that balance exploration and exploitation. By exploration, we mean searching the part of the design space that has much uncertainty. By exploitation, we mean searching the area in the proximity of the current best solution. The need for quantifying the uncertainty about the response surface makes the Gaussian processes the most popular class of surrogates. So let's recall that the posterior distribution of a Gaussian process can be derived in closed form, and its computation can be reduced to simply linear algebra. This line of research is closely related to Bayesian optimization in the machine learning literature, where a primary motivation is the so-called hyperparameter tuning of sophisticated machine learning algorithms or models. So in the following, I will cover 3 algorithms. All of them share the following general structure. It consists of basically 6 steps. The first, we impose a Gaussian process prior on the unknown function f. And second, we select the next batch of design points subject to a prescribed criteria that is computed using the current belief about the f. Third, we run simulation experiments at each of the newly selected design points. And fourth, we update the Gaussian process posterior given the new observations. And then we repeat the steps 2, 3, 4 until the simulation budget is exhausted. And finally, we optimize the posterior mean function using any numerical optimization algorithms, and then return the solution as the solution to the original simulation optimization problem. So as you will see just in a minute, all these methods, they mainly differ in the second step, which is how to select the next batch of design points. So the first algorithm that I'll introduce is called knowledge gradient. So knowledge gradient methods were originally proposed to solve ranking and selection problems, but later it was generalized to the continuous setting. So let's recall that given the observations at n design points, the posterior of the unknown function f is a Gaussian process with whose mean function and covariance functions can be computed in closed form. The KG method selects the next design point, xn+1, by maximizing the so-called KG factor, which is defined as follows. So the interpretation of this KG factor is as follows. If our simulation budget were exhausted after collecting the data d of n, then we would use the maximum over the maximum of mu n as an estimate of the maximum value of the function f. However, now that we are allowed to run one more simulation experiment at xn+1, the posterior mean function will become mu of n+1 after the new data point xn+1, yn+1 is added to the dataset. Therefore, the increment in the estimated maximum value of the function f is simply this difference. Before the simulation is run at xn+1, this mu of n+1 is in fact a random quantity, conditional on d of n. And its distribution is determined by the updating equation. So in particular, conditional on the data d of n and xn+1, this mu of n+1 has a normal distribution that depends on x, while the mu of n is simply a constant. So basically, what this means is that in principle, we can compute the expectation of this difference because we know what the distribution of this we know what distribution that determines this random quantity. Having said that, to do so, having said that, both the computation of this KG factor and its optimization is far from trivial. In Scott, Fraser, and Powell 2011, the authors proposed a discretization scheme to find an approximate solution of this to maximize this KG factor. And later in Wu and Fraser of 2016, they view the task of maximizing the KG factor itself as a stochastic optimization problem, and propose to use stochastic approximation to do the task. That's because under moderate technical conditions, it can be shown that the gradient of this KG factor with respect to x can be written as the expected value of the gradient of this term. So the second algorithm, globally convergent algorithm that I would like to discuss is the upper confidence bound method, or UCB. UCB is a very popular class of methods for multi-arm banded problems. So similar to the ranking and selection problems, MAB problems are also concerned with finding the optimal among a finite set of alternatives with unknown performances or unknown rewards. The key difference between MAB problems and the ranking and selection problems lies in the objective. So basically, the banded problem can be viewed as an online decision-making problem that aims to maximize the cumulative rewards that are collected over entire time horizon. In contrast, the ranking and selection is more of an offline flavor. It aims to maximize only the terminal reward at the end of the time horizon. So in 2012, in this paper by Surrogates, the UCB method was analyzed to the continuous setting, where the objective is to maximize a Gaussian process sample path. And the method is called GPUCP. So the structure of GPUCP is largely similar to knowledge gradient method. The main difference is regarding how to select the next design point x of n. So in the GPUCP method, the next design point after collecting n data points is to maximize a different function, which is we call it UCB score. So both UCB score and the KG factor that you saw earlier are called the acquisition function in the machine learning literature. So when you look at this UCB score, it clearly shows the trade-off between exploration and exploitation. That's because if you want to find, that's because a design point is favored based on the UCB score, either because it has a higher value in the posterior mean, which corresponds to exploitation, or it has a higher value in the posterior covariance, which corresponds to exploration. Evidently, this UCB score is much easier to maximize than the KG factor because the UCB score does not involve the computation of exploitation. However, a potential downside of the UCB method or GPUCP method is the existence of this tuning parameter gamma. It turns out that the practical performance of the GPUCP method depends critically on the choice of this tuning parameter gamma. So in a typical setting of multi-unbounded problems, the tuning parameter gamma is often said to be of order log n. But in the setting of simulation optimization, because we look for because we try to maximize the terminal reward and ignore all the intermediate rewards along the way, conceivably we should explore. We should do more exploration than it would require for the MAB problem, and that means that there may be a better choice of this tuning parameter gamma m in simulation optimization problem, and but this issue is yet to be addressed. So now let's make a very quick summary about the difference, the key differences between GPUCP and knowledge gradient. So as I mentioned, the KG factors and UCP scores are referred to as acquisition functions. And for GPUCP method, the maximization of the acquisition function is much easier than knowledge gradient. But the GPUCP involves a tuning parameter which may be hard to do to tune in practice, whereas the KG does not involve any tuning parameter. So a third globally convergent algorithm that I would like to cover is the GP-based search, or GPS method. Okay. So a key difference between GPS method and the other two is that the GPS method uses a sampling distribution instead of acquisition function to determine the next batch of sampling, the next batch of design points. The GPS method is belong to this general class of random search algorithm that sample randomly a number of design points in each iteration, based on a so-called sampling distribution that may be updated based on all information collected through the optimization process. One of the critical issues in developing random search algorithms for simulation optimization problems is to design a good sampling distribution that automatically balance exploration and exploitation. So similar to the UCP method, the GPS algorithm also uses the posterior mean function and the posterior variance to guide the balance between exploration and exploitation. But it uses this notion of probability of improvement to do so. So here, the f star of n denotes the current estimated optimal value. And because the f of x under the posterior distribution has a normal distribution with such a mean and such a variance, so this is the event that the function value is greater than or better than the current estimated optimal value. And this will be the probability of improvement. And the sampling distribution of the GPS method is simply a probability distribution that is proportional to this function. And in each iteration, this GPS method will draw a batch of design points from this distribution. However, generating random variables from distribution that is only known up to a constant is generally hard. And in Hong and Hu of 2014, they proposed to use a Markov-Chain multicolor method to do so. But later, the same group of people proposed to use a Gaussian mixture to approximate the distribution, which is much easier to generate from. So now I want to highlight the key differences between the GPS method and the KG or GPUCP method. So the GPS method uses a sampling distribution to generate a batch of design points in each iteration. In contrast, the knowledge gradient or GPUCP method uses acquisition function, so either KG factor or UCP score, to determine one design point at a time in each iteration. Okay. So now let's move on to the final part of this tutorial, computation for large datasets. We have taken for granted so far in this tutorial that surrogates are computationally fast, and rightly so in light of their analytical tractability. However, this assumption is challenged when the number of design points is large because the computation of surrogates, especially Gaussian process regression, usually involves numerically inverting a large matrix, such as highlighted here. So it is well known that the time complexity for matrix inversion scales at a rate of n to the power of 3, and the space complexity scales like n squared. So this means it quickly becomes computationally even infeasible when n is large, even in modern computational infrastructures. The need for processing large data sets calls for approximation methods to reduce the computational burden caused by numerical inversion of large matrices. There is a huge literature on approximate computation for Gaussian processes. And here we present two popular ones, the knife draw method and the random features method. Both methods have drawn substantial interest in recent years. Both methods actually are built upon the following idea using Lowrank approximation and Woodbury formula. So let's suppose that we are interested in approximately compute this inverse matrix, where let me remind you that the K is a covariance matrix and sigma is a diagonal matrix. So now the trick here is to consider a matrix K tilde that has a lower rank than n. For this low rank matrix, it can be expressed as the multiplication of three matrices of compatible divisions, of compatible dimensions. The famous Woodbury formula states that the inverse of this K tilde plus sigma can be written as follows. The key here is that by using this formula, the computational bottleneck has been transformed to the computation of the inversion of a smaller matrix of size n by m instead of n by n. So therefore, to take advantage of this low rank approximation, the Woodbury formula, our job here is to find or construct another kernel K tilde, which will lead to a low rank matrix approximation. So now let's first take a look at the natural method. In this method, we are going to select m out of the n design points, okay, and then define a vector km and a matrix kmm in the following way, based on using the selected design points. And then we can define a different kernel K tilde in this way. Okay. If we do so, then it can be shown easily that the covariance matrix associated with evaluating this K tilde, this different kernel at the original n design points, is a low rank matrix. This matrix is of size n by n, but it has a rank m. So then we can take advantage of the Woodbury formula, essentially in the same way that you saw earlier, to show that the posterior distribution of the Gaussian process with this new kernel Q tilde shares can be computed with much smaller time complexity. So again, the key idea is that after this approximation, the matrix inversion occurs to a smaller matrix of size m by m rather than n by n. The second method, random features, represents actually a large class of algorithm. There are a lot of variations since the publication of this paper in 2007. So in the following, I'm just present this original version of the random feature method, which the authors call random Fourier features, RFF. So RFF applies in particular to stationary kernels, including the Gaussian and Matin class of kernels. So the reason is, if K is a stationary kernel, then Buckner theorem in functional analysis asserts that it can be the kernel can be represented as the Fourier transform of a probability measure P. So for example, if the K is a Gaussian, then the P is multivariate normal. If K is Matin, then P is multivariate T distribution. So given this Fourier transform, we can do further derivation. For example, we because this kernel is real valued, then we can discard the imaginary part of the Fourier transform and only keep the real part, and then further we can express it as the expectation with respect to this probability distribution. We can further use some simple calculation to show that if we define a random variable B as a uniform random variable, then we can express the same expectation as the following, which is the key here is it is the expectation of a product of two terms, one involving x, the other involving x prime. This form of factorization has the following advantage. Given this expectation, we can use Monte Carlo approximation to approximate it with a sample average. And because of this factorization, we can write down this sample average as the a inner product of two vectors, phi of x and phi of x of prime. And this effectively defines a different kernel, K tilde. Okay. The reason why this method is called random features is because this phi is effectively serve the same purpose as a set of basis functions. And in machine learning, basis functions are also called features. Okay. And because these features are determined randomly, they're called random features. So it can be shown very easily that the convergence matrix associated with evaluating this new kernel is a low-rank matrix. Okay. So now let's make a very quick comparison between these two methods. The Nastrom method, for it to work, we need to select a smaller set of design points. So therefore, the Nastrom method is data dependent. So here the data refer to the design points. By contrast, the RFF method does not need to make any selection among the design points. In fact, it does not involve design points at all. So RFF is data independent. However, RFF only apply to a set of kernels. So particular, most of the random feature methods only work for stationary kernels. And in contrast, the Nastrom method is kernel independent. It applies to all kernels. So now we come to the end of this tutorial. Let's quickly summarize. We have introduced several typical surrogates, including low-order polynomials, linear basis function models, and the Gaussian processes. We also discuss simple techniques to enhance their prediction capability with a little additional computational overheads, including using stylized models or gradient observations. We also covered several algorithms, including locally convergent algorithms such as RSM or strong algorithm, and globally convergent algorithms such as knowledge gradient, GPUCP, and GPS. Finally, we have discussed two widely used methods for dealing with computational challenges associated with Gaussian processes in the presence of large datasets, and they are the natural method and the random features. Looking forward, we believe that the following research directions are potentially of high impact. First, an ideal simulation optimization algorithm, in our opinion, should be able to quickly identify most local optimal solutions and then select the best among them. In contrast, it is often observed in practice that globally convergent algorithms, such as those introduced in this tutorial, tend to overexplore. Lack of gradient information to provide local curvature of the response surface is an important reason. Therefore, it is of great interest to develop algorithms that can integrate local search with global search to ensure a faster convergence to global optimal solution. Second, another possible approach to accelerating convergence to global optima is to incorporate structural information, such as monotonicity, convexity, and smoothness. The surrogates that possess such properties do exist, but how to leverage them to develop fast algorithms is yet to be fully addressed. And the third, most theoretical analysis of simulation optimization algorithms in the literature focus on providing convergence to local or global optimum as the computational budget grows. Such asymptotic analysis can hardly explain the finite performance of the algorithm. Therefore, we believe that a deeper theoretical understanding of these simulation optimization algorithms, such as the radial convergence, or even finite performance analysis, is strongly needed to fill the gap, as it may shed some light on critical properties or attributes that are required to improve the algorithm's efficiency. And finally, we believe that parallel computing is a promising direction. Running simulation experiments is often time-consuming, but different simulation experiments are typically independent with each other, and they can be run on different processors. So we believe that there are a lot of opportunities in developing efficient surrogate-based parallel simulation optimization algorithms. Thank you. That's all.